Alright, in this part we will go into finding the particular integral. So we have a second order linear differential equation with constant coefficients, and it is inhomogeneous where g of x is not equal to 0. Now g of x can take many forms, but we will look at a certain set of forms and we will set up a table. G of x. So g of x can be a constant, it can be a first order polynomial, it can be a second order polynomial, and it can be an nth order polynomial. So it doesn't really matter what order polynomial it is. It could be something with a cosine of kx, it could be something of a sine of kx, and it could be e to the power of kx. To find the particular integral, we first choose a trial solution. And the trial solution we will pick based on this form. So if it is a constant, we choose a constant. If it is a first order polynomial, we choose a first order polynomial. Second order polynomial, we choose a second order polynomial. An nth order polynomial, exactly the same. If we have something with a cosine of x, we choose something with a cosine of kx plus something with a sine of kx. Same goes for a sine, we choose something with a cosine of kx plus something of the sine of kx. And if we have an exponential function, we will choose this same exponent with a coefficient. Now, a very, very short background about this. So how do we come to this set? Well, if we take our inhomogeneous part and we keep differentiating it and collect together the different parts we find, that's how we get to here. So if we have a constant and its derivatives, but its derivatives are 0, so we're left with a constant. A first order polynomial, if we differentiate that, then we get a constant, so we get something with an x and something with a constant. Same goes for here. Now, when we have the cosine, if we differentiate that, we'll get something with a sine. And then if we keep on differentiating, something with a cosine and a sine with again. So the different parts are something with a cosine and something with a sine. Same goes for the sine. We get something with a cosine and something with a sine. If we differentiate e to the power of kx, we still get something of e to the power of kx, just with a k in front of it. And we amass all those derivatives in a single form. Well, this background is not important for us at the moment. It's just that if we know we have a certain inhomogeneous part, we know what trial solution to pick. Now, there is something about the exponents. So if we have our homogeneous solution, YH, that is some constant e to the power of lambda 1 x plus c to the 2 e to the power of lambda 2x. These lambda 1 and this lambda 2 are the roots. All right, this lambda 1 and 2 are the roots of the auxiliary equation. Now, if k is lambda 1 or lambda 2, so if k is one of the roots of our auxiliary equation, we don't take this. No. We take ex e to the power of kx. So if lambda 1 and lambda 2 are different, but this k happens to be one of them, we don't take this one because that is one of the solutions to the homogeneous equation, and that will never end up being gx. We have to add an x. Now, should lambda 1 and lambda 2 be exactly the same, and also exactly the same as k, then we add an x squared, but this case hardly ever arises. But this one, where it is one of the two, that can happen, and we just add an x there. So how does it work? So if we have, for example, y double prime plus y prime minus 2y is equal to x squared, we have a second order equation, and we try as our trial solution ypi of x is ax squared plus bx plus c. If we have, well, the same equation here, e to the power of 3x, 3 will not be one of its two roots of the auxiliary equation. We try y pi of x is c. Well, I used an a before, I'll use an a again, but the letter obviously doesn't matter. A e to the power of 3x. Should we have our root, let's see, e to the power of x. So 1 is indeed one of the roots here. Then we have our particular integral, x would be a x e to the power of x. So these are our trial solutions. Now how do we get to these values of a, b and c? Well, we find these values once we plug this particular integral back into the differential equations and then solve for these constants, which I will do first for this example, then for this one, and then for this one. So this is our trial solution, and we want to find values for a, b, and c. Well, for administrative purposes, I always write out the two derivatives, 2ax plus b, and the second derivative of my trial solution, which will be 2a, and that just gives me an overview of what I am going to fill in the original differential equation. So it is 2a plus 2ax plus b minus 2 times this, so that's minus 2ax squared minus 2bx minus 2c, and that has to be equal to x squared. Now I have terms with x squared, I have terms with x, and I have my constant terms. And that has to be equal to x squared, well, actually x squared plus 0x plus 0. So I'm going to match the x squared terms left and right, the x terms left and right, and the constant terms left and right. I am left with three equations. Minus 2a is equal to 1, 2a minus 2b is equal to 0, and 2a plus b minus 2c is equal to 0. Well, from the first equation, I can see that a is equal to minus 1/2, and I can fill that in here, and I get that minus 1 minus 2b is equal to 0. That gives me b is equal to minus 1/2 as well. I filled it in the last formula, so we get 2a, which is minus 1, plus b minus 1/2, minus 2c is equal to 0. We find that minus 3 over 2 is equal to 2c, and we find c is equal to minus 3 over 4. So we found our coefficients, and we find that the particular integral is then equal to minus 1/2 x squared minus 1/2 x minus 3 over 4. Now it is very important that we take the full second order polynomial. If we just had, say, oh, we have here an x squared, we take ax squared, you'll see that you'll run into trouble because you cannot match the a's here with the terms for x and the constant term. So you need the full second order polynomial. Now for this one we find the particular integral, we know what the homogeneous solution is, we add the two together and we get our final solution. So this is an example for a second order polynomial. So let's see what happens with an exponent that is not one of the roots. Because if we quickly look at the auxiliary equation for the homogeneous differential equation, we get lambda squared plus lambda minus 2 is equal to 0. That is lambda plus 2 times lambda minus 1 is equal to 0. Lambda is equal to minus 2 or lambda is equal to 1. So these are the roots of the homogeneous polynomial. And now let's look at e to the power of 3x and see what our particular integral will be there. Well, it is an exponent where k is not one of the roots. So we can write out that our trial function is equal to a e to the power of 3x. Again, I write out the two derivatives. I write out the second derivative and I plug this into the differential equation. So I get 9a e to the power of 3x plus 3a e to the power of 3x minus 2a e to the power of 3x, and that should be equal to e to the power of 3x. Now these are all terms of the form something times a to the power of 3x. I have 9 plus 3 minus 2 is 10 a e to the power of 3x, which has to be equal to this, which means that a is equal to 1 over 10. My particular integral is therefore 1 over 10 e to the power of 3x. If I know my homogeneous solution, which I can write out from here, that is equal to c1 e to the power of minus 2x plus c2 e to the power of x. My complete general solution, y of x, is then equal to the c1 e to the power of minus 2x plus c2 e to the power of x plus that 1/10 e to the power of 3x. So my homogeneous solution plus my particular integral. Now there's something very important here, is that I still have coefficients here. And remember, this is the general solution of a differential equation. I have a particular integral, but don't confuse that with the particular solution. If I had initial conditions, like y0 is 1 and y prime 0 is 1, then I could calculate these coefficients. But the homogeneous solution without those initial conditions will contain our two constants, our two integration constants, and our particular integral after calculation will not contain a constant. So that is very important, that you get the constants in the homogeneous solution, but not there. So this is another form of a particular integral, and I said I would do one more, and that is for the case that we don't have e to the power of 3x, but we were, for example, to have e to the power of x. Now, 1x is one of my roots, so I don't choose this one. I choose this as my trial solution, ypi, so that my trial solution is ax e to the power of x. And then we'll again write out its derivatives. This is ae to the power of x plus ax e to the power of x by using the product rule. And the second derivative is 2ae to the power of x plus 2ax e to the power of x, where I've the derivative of this one is a to the power of ex, and the derivative of this one is ae to the power of x, so I add that to that one, plus ax e to the power of x. Well, let's put this into the differential equation. So the second one, 2a e to the power of x plus ax e to the power of x, plus the first derivative, so this one, plus a e to the power of x plus ax e to the power of x. So if I use colors, then the second order is this bit. The first derivative is this bit, and I will get some blue, minus 2a e to the power of x, and then we have this one there. So we've plugged it all into the equation, and our goal here is to find the value of a. Well, I have 2a e to the power of x plus 1 a e to the power of x, and that's it. So I have 3a e to the power of x. We have a to the power of ax e to the power of x plus ax e to the power of x minus 2. Let me do this properly. Sorry, minus 2ax e to the power of x, because I forgot that. 1 plus 1 minus 2 is equal to 0. So that term drops out, and it has to drop out because otherwise we'd be in trouble. And we find a is equal to 1 over 3. So my particular integral is 1/3 e to the 1/3 x e to the power of x. My total solution would be then y of x is equal to c1 e to the power of minus 2x plus c2 e to the power of x plus 1/3 x e to the power of x. And that is this case here. Well, the same goes for sines and cosines. And then there's only one more thing to say, that what if my gx is x minus 2 sine of 3x? Well, this isn't in this table here, but it is a combination of inhomogeneous parts. And if we have a combination of inhomogeneous parts, we take the combination of trial solutions. So this is a linear, a first order polynomial. So we take a first order polynomial, and we have something with a sine of 3x plus something with a cosine of 3x, and it is essential not to reuse these letters. So if you use an a and a b here, you cannot use an a or a b here. You keep using different letters. So to summarize, to find the particular integral, you look at the form of the inhomogeneous part, you select a trial function, write out its derivatives for administrative ease, put it into the differential equation, solve for the constants in your trial function, and as a general, the general solution is then adding that homogeneous part to our particular integrals, which will not then have a constant there. So this is how you find the solution to an inhomogeneous second order linear differential equation with constant coefficients.